we've already accomplished teleportation. It's been a prediction of quantum theory for decades. We've successfully teleported small particles, but can we do it with larger objects? The answer is still uncertain, but teleportation has been achieved with the smallest particles. Recently, reports emerged claiming something impossible occurred in an MIT quantum lab. A particle was supposedly teleported across their system, creating a ghost copy back at its origin. This means two identical quantum states existing at once, which physics says can't happen. What makes this claim terrifying is MIT's team pushing boundaries that others won't touch. They've simulated wormholes using quantum computers and entangled particles across vast distances. Additionally, they've been utilizing AI systems to control experiments in unprecedented ways. If even a fraction of these reports are true, we're not just looking at a lab error. We might be witnessing a violation of the most fundamental rules of reality itself. The no-cloning theorem, a principle unbroken for over 40 years, may have just cracked. Some researchers who heard these whispers used a phrase that chills any physicist's spine: they went too far. Consider this: if quantum information can duplicate, particles might leave ghost copies behind. This could mean we need to rewrite everything we understand about secure communications, quantum computing, and the fundamental fabric of space-time itself. But what exactly could cause a quantum ghost to appear? And why are some scientists now afraid that we've opened a door we can never close? Here's what most people don't realize about quantum physics. We've observed particles leaving traces that shouldn't exist. They cool atoms to nearly absolute zero, manipulate their quantum states, and observe. The atoms should lose all their quantum properties instantly, but they don't. Faint traces linger, ghostly signatures persisting for seconds, sometimes even minutes. This occurs after the original state was supposedly destroyed. Then there's quantum ghost imaging, where entangled photons photograph objects. The photons hitting the object don't contribute to the image at all. It's as if the object is seen by its quantum ghost. This isn't just theory, it's happening in labs around the world. In nuclear magnetic resonance facilities, researchers see quantum echoes regularly. A signal disappears completely from their instruments, gone. Quantum information somehow stored itself in hidden degrees of freedom and came back. We already know quantum systems can leave strange traces behind. Information that should vanish can hide and resurface. Particles can interact with objects they never touch. The universe keeps quantum backups we didn't know existed. What if MIT's teleportation experiment discovered the most extreme version of this phenomenon? What if they uncovered something that challenges our very understanding of the universe? Imagine deleting a file on your computer. It vanishes, right? But then, moments later, it reappears without you hitting undo. That's the essence of this quantum afterimage. A state that was meant to be destroyed somehow resurrects itself. If quantum information can duplicate, every secure communication system on Earth is suddenly vulnerable. And if that's the case, it's not just physics at stake. Here's why this matters beyond the lab. Quantum teleportation is not merely a physics experiment. It serves as the backbone of the most secure communication system ever designed. When you teleport a quantum state, it becomes completely unhackable. Any attempt to intercept or copy the data destroys it instantly. China, Russia, and the US are racing to build quantum communication networks. Whoever controls these networks will control the future of secure information. But if quantum states can leave ghost copies behind, that changes everything. Imagine sending classified military data through quantum teleportation. You believe it's impossible to intercept. But what if a faint quantum echo lingers at the transmission point? What if that ghost contains enough information for an enemy to reconstruct your message? DARPA has invested billions in quantum communication research. The NSA has entire divisions dedicated to quantum cryptography. If even the possibility exists that teleported information leaves traces, every intelligence agency would want to know immediately. And here's the terrifying part: China is already ahead in this race. In 2017, Their Misha satellite successfully teleported quantum states from Earth to orbit, over 500 kilometers away. They've built quantum communication networks spanning thousands of miles across their territory. Most Americans might not even know we are fighting this battle. Before I show you how MIT's Ghost connects to wormholes and reality itself, make sure to hit subscribe. You don't want to miss what's coming. Remember, this wasn't supposed to happen. The laws of physics explicitly forbid quantum information from duplicating itself. And yet, MIT may have stumbled upon a doorway into something far stranger than science predicted. What they found next suggests we're not just dealing with a communication security issue. We might be looking at evidence that reality itself has backup systems we never knew existed. Now, here's where things get mind-bending. MIT's quantum team wasn't just conducting standard teleportation experiments. In 2022, they collaborated with Caltech and Google to create something unprecedented. They didn't rip open space-time, but they did send quantum information through a wormhole-like structure. The researchers described it as quantum information traversing a bridge through space-time. What if MIT's later experiments were still operating within that regime? What if researchers are still exploring the boundary between quantum mechanics and space-time geometry? If you're manipulating quantum states in ways that resemble wormhole physics, you could unintentionally create effects. They are proposing something called time-lagged quantum echoes. The idea is that quantum information could re-emerge. Not instantly, but after a delay. It's as if the universe has a memory replay button. This activates on its own schedule. This connects to one of physics' biggest mysteries, the holographic principle. The theory suggests that all the information in any volume of space can be stored on its boundary, like a cosmic backup drive. If that's true, every quantum state that ever existed leaves an imprint. Leaves behind a ghost copy? Not just in the lab, but embedded in space-time itself. Here's a question for you. If a ghost copy of a particle can reappear, could a ghost copy of a thought, or even a person, exist too? Drop your take in the comments before we explore the implications. How far this idea could really go? Rehook at 5 minutes. Because what MIT may have glimpsed isn't just a glitch in their equipment. It could be the first proof that reality has layers. Quantum layers that overlap and interact in ways we never imagined possible. The human impact. Let's make this personal. If quantum information can leave ghost copies, imagine what that means. For everything we think we know about permanence. Every photo you've deleted, every text message you've sent, every memory you've forgotten. What if none of it ever truly disappears? What if it's all still there? Stored in quantum layers of reality? We're just now learning to detect this. Scientists already believe consciousness might emerge from quantum processes in the brain. Then maybe our thoughts, our memories, our very sense of self, could persist in ways we never imagined. Consider digital resurrection. Right now, when data is erased, we assume it's gone forever. But if MIT's discovery proves that quantum information leaves recoverable traces, we might be able to restore anything. Conversations with deceased loved ones, lost works of art, historical records that were thought destroyed. It's awe-inspiring and terrifying at the same time. Every mistake, every secret, every moment of your life might be permanently archived in quantum structure of space-time. Think of your own life. Every memory you've ever had. Every thought you've lost. What if they're still out there, imprinted somewhere in the quantum fabric of reality? That's the kind of question MIT's Ghost forces us to ask. But there's an even more unsettling possibility. If teleportation technology ever advances to complex objects, and if ghost copies can appear, the implications of this discovery could reshape our understanding of reality itself. Imagine being transported and duplicated, creating two versions of yourself. Both individuals have identical memories, each convinced they are the original. And if that doesn't send chills down your spine, consider this. This ghost effect might already be happening in quantum experiments worldwide. We just haven't been looking for it until now. Understanding this process makes MIT's alleged ghost even more extraordinary. Picture three characters: Alice, Bob, and Charlie. Charlie is the particle whose quantum state Alice wishes to send to Bob. Alice and Bob share an entangled pair of particles, like quantum twins. These particles are mysteriously connected, no matter the distance. This action completely destroys Charlie's original state. However, the measurement creates two classical bits of information. These bits act like a recipe for Bob to recreate Charlie's state. Alice sends those two bits to Bob through normal communication. When Bob receives them, he performs a specific operation on his particle. If everything works perfectly, Bob's particle now holds Charlie's original quantum state. The information has been teleported successfully. The crucial point is that Charlie's original state is now gone, destroyed. The no-cloning theorem states you cannot make perfect copies of unknown quantum states. Teleportation works because it's cut and paste, not copy and paste. This process has been proven repeatedly over the years. In 1997, researchers first teleported a photon state across a lab bench. By 2002, teams were teleporting states without physical connections. In 2017, quantum information was teleported from Earth to orbit. Each breakthrough confirmed the same principle: the original state vanishes. There are no exceptions to this rule. MIT's experiments go beyond simple communication. Their 2022 wormhole simulation probes the deepest foundations of physics. This relates quantum mechanics to space-time geometry itself. When testing theories at this frontier, unexpected effects may arise. MIT's quantum afterimage might never appear in a peer-reviewed journal. If the anomaly is real, it represents something unprecedented in physics. Physics has revealed glimpses of phenomena we weren't meant to see. Perhaps this is essential for advancing human understanding. The universe may contain layers beyond our imagination, including concepts like quantum backup systems. These systems preserve information even after destruction, suggesting a reality that possesses memory. So, what do you think? Did MIT stumble upon a forbidden corner of physics? Or is this merely the first hint of a breakthrough too significant to reveal just yet? Either way, make sure to subscribe so you won't miss the moment we discover the truth. Whether MIT's quantum ghost was genuine or not, we are in an era where the impossible is becoming routine. Imagine particles teleporting across continents and information traveling through simulated wormholes. Quantum computers may soon tap into parallel realities, opening up new dimensions of possibility. The next breakthrough could emerge from any lab at any moment, changing everything we know. And when it happens, you'll want to be prepared to comprehend its implications for all of us.